Consider the following matrices, and here we are given two 2x2 matrices. We have matrix A and matrix B. And now here we're asked to specifically use the row-column rule to find the following products. So in part A, we're asked to find the product matrix A times matrix B. And in part B, we are asked to find the product of matrix B with matrix A. Now, before we get started, let's quickly recall the row-column rule for matrix multiplication. So we need to go ahead and assume that these two matrices are size appropriate. So we'll let matrix A be an M by N matrix, and we'll let matrix B be an N by P matrix. So we can see that the number of columns in the first matrix matches the number of rows in the second matrix, meaning that the product AB exists. Woohoo! We can also see that this new product is going to have a size of M by P. So to remind ourselves about the row-column rule, let's consider the ith-jth entry of this product. So we have the ith row of matrix A multiplied by the jth column of matrix B, which is computed by taking the sum of the product of the corresponding components. So here is our beautiful row-column rule, and we're going to use this now to find the product of matrix A times matrix B, and then matrix B times matrix A. So in part A, we are asked to find the product of matrix A times matrix B. And now we can see that this exists because matrix A is a 2x2 matrix and matrix B is a 2x2 matrix. So the number of columns of the first matrix matches the number of rows of the second matrix. Woo! So AB exists and we're ready to go. So here we go. We have matrix A multiplied by matrix B. Now matrix A is defined as 1, 2, 3, 4. And matrix B is defined as 5, 6, 7, 8. So we want to apply the row-column rule. So we are going to take each row of matrix A and multiply it by each column of matrix B. And let's look at this full out in detail this first time through. So we are taking the first row of matrix A and multiplying it by the first column of matrix B. And then again taking the first row of matrix A and multiplying it by the second column of matrix B. So here we go. We have the first row of matrix A, 1, 2, multiplied by the first column of matrix B, 5, 7. We then again have the first row of matrix A, 1, 2, multiplied by the second column of matrix B, 6, 8. Beautiful. Now, we want to go ahead and do the same thing with the second row of matrix A. We are taking the second row of matrix A and multiplying it by the first column of matrix B, and then again taking the second row of matrix A and multiplying it by the second column of matrix B. So putting this into play, we have the second row of matrix A, 3, 4, multiplied by the first column of matrix B, 5, 7. And last but not least, we have the second row of matrix A, 3, 4, multiplied by the second column of matrix B, 6, 8. Beautiful! So now we're ready to perform the dot product in each case. And we'll give ourselves plenty of room. So here we go. The first entry, the first row, first column of AB will be 1 times 5 plus 2 times 7. Now the entry in the first row, second column, will be 1 times 6 plus 2 times 8. Moving to the second row, so we have the entry in the second row, first column, will be 3 times 5 plus 4 times 7. And last but not least, the entry in the second row, second column, will be 3 times 6 plus 4 times 8. So we've performed the dot product, and now it's just a little arithmetic. So what are we left with here? We have 5 plus 14, and then 6 plus 16. We then have 15 plus 28, and 18 plus 32. And so therefore we can see our beautiful final answer for matrix A times matrix B will be 19, 22, 43, 50. So that is the final answer for part A. But we're not done yet. We now want to go ahead and perform a similar computation in part B to find the product of matrix B with matrix A. And as always, we'll check for our safety. We have matrix B again is a 2 by 2 matrix, and we have that matrix A is a 2 by 2 matrix. So we can see that the number of columns of matrix B equals the number of rows of matrix A, and so therefore the matrix B times A exists. Woohoo! So here we go, and let's give ourselves a little bit more room. So now we are performing the computation in the opposing direction. We have matrix B times matrix A. So matrix B is defined as 5, 6, 7, 8. And matrix A is defined as 1, 2, 3, 4. Now again, we're using the row column rule here. So we want to take the first row of matrix B and multiply it by the first column of matrix A, and then take the first row of matrix B and multiply it by the second column of matrix A. So writing this out, we have the first row of matrix B, which is 5, 6, multiplied by the first column of matrix A, 1, 3. And again, we have the first row of matrix B, which is, again, 5, 6, multiplied by the second column of matrix A, 2, 4. And now we want to go ahead and do the same thing with the second row of matrix B. So we're going to take the second row of matrix B and multiply it by the first column of matrix A. We'll then take the second row of matrix B and multiply it by the the second column of matrix A. So we have the second row of matrix B, which is 7, 8, multiplied by the first column of matrix A. And then again, we have the second row of matrix B multiplied by the second column of matrix A. And we're ready for the dot product. So this leaves us with, in the first row, first column, we have 5 multiplied by 1 plus 6 multiplied by 3. In the first row, second column, we have 5 multiplied by 2 plus 6 multiplied by 4. In the second row, first column, we have 7 multiplied by 1 plus 8 multiplied by 3. And last but not least, the entry in the second row, second column, we have 7 multiplied by 2 plus 8 multiplied by 4. Lovely. So now all that's left is a little arithmetic. So we are left with, we have 5 plus 18, 10 plus 24. We then have 7 plus 24, and 14 plus 32. So we are left with a beautiful final answer for matrix B multiplied by matrix A. We have 23, 34, 31, and last but not least, we have 46. And so this is our beautiful final answer to part B. And now, I love this example because it's pointing something out to us. We can see here that matrix multiplication, in general, is not commutative. And we can see that because matrix AB does not equal matrix BA. So I want you to exercise caution. And we say that in general, matrix multiplication is not commutative. Right, so in other words, matrix A times matrix B does not necessarily equal matrix B times matrix A. We'll have a special case when they are equal, as we'll see in the very next section, but again, in general, matrix multiplication is not commutative. So with this cautionary advice, let's go ahead and look at some of the standard rules and algebraic properties for matrix multiplication.